part two. It is time for part two today. So let's see here. We will show our board. Hello everybody, welcome, welcome. How is everybody today? Put these over here. Turn it around to say hello. So hello, welcome. Today's part two. Hi Linda. Victoria, I'm glad you could make it. Today we're doing quantum as requested by Victoria, but we get to roll it in right into lasers because it's very relevant and important. Good morning, Mark and Matt. Another physicist. Oh my goodness. Hello. I think you may be the first physicist that I've seen on here. So welcome. Nice to meet you. I'm Julia. Yes, another Victoria. Hi, Victoria. Lasers indeed. And so this is fantastic. I'm sorry, actually, I just followed you and I didn't catch your name, the other physicist. So this is great. We got two. We had someone who was interested in or who studied photonics in here yesterday. Maybe he'll come back. I believe that was Alex. So yeah. Hey, Parker, it is. Hey, Nick, welcome. And Chris, oh, so many familiar faces. Hi, went out to play. Haven't got your first. Jennifer, I'll try to remember that. Lindsay, oh, thank you. Welcome, Lindsay. Nice to see you. Thank you for stopping by. So today is part two. We'll do a quick review here in just a second of what we went over yesterday. And then we'll do part two of, hi Nick, of the quantum part of the lasers. So you're doing a master's in cosmology. Okay, so DC Hooper, I need to first find your first name here. Deanna, it is lovely to meet you, and I need your help because I am a laser scientist, laser physicist, and so yeah, thank you. There definitely are someone. Ian also. Ian is a neuroscience grad student, so he does stuff also I can't discuss, I can't even touch, but I will certainly need your help in cosmology because there is so much interest in it, especially with the Pluto flyby and all of that, and my expertise is not in it, and I think, and I need to brush up, so that's wonderful. Nice to meet you. So how does it feel to have a PhD? It's a relief. I think that would be the biggest response I could have is a relief because it was a lot of work. Hey Scott, lasers indeed. Yeah, it was a lot of work. It's nice to have it. I think it was quite a journey, and I learned a lot of things that I didn't even expect to learn, and that had nothing to do with science also, but I also learned a lot about how to learn. So it feels good to be on this side of it. Only recently though. So all the brain power. Yeah, absolutely. Not through osmosis. Linda, we're gonna talk about it and then we'll relax afterwards with Linda's lovely knitting session. So yes, so we'll get right into it so we don't take too much time. I did get your message, Victoria, and so I'm gonna judge see news today, white laser. So interesting. So there are white lasers. White lasers are not easy to make, and we can talk about that in a little bit because white light, that's kind of confusing maybe if you understand some of what we were saying yesterday in that we were talking about lasers having one color, one wavelength, and white light is all the colors mixed together, and so that is counterintuitive. And so we can get into tomorrow, top post on Reddit. Okay, I'll check it out. I'll see what the article is. Thanks, Scott. Because the tomorrow's topic, so part 3 of 3, I think I'm going to talk about the types of lasers that exist and how they're used. So today we'll do kind of a final wrap up of the innards of a laser and what makes it so special and cool. Hey, Chuck. And then tomorrow I'll talk about some of the applications and where the lasers, where the laser technology is and how we use them. So I'll flip this around quickly. I'll show a brief. Oh, well, thank you very much. So that's kind of a brief, that's where we left yesterday. I'll probably erase most of this, or at least move it out of the way. But we were talking about light bulbs here. We were talking about the amplification. Good morning, Jason. Nice to see you. Talking about the amplification, these waves all being nicely laid on top of each other and having the same wavelength, being what we call coherent or in phase. And then the exciting of the energy. So the quantum part is we're going to get into how do we get all of these the same energy here, and I'll let kind of the audience and Victoria, we can talk. Victoria had sent me a lovely tweet with a screen capture from a book talking about all this fancy math that has to go into this, and it does get a bit complex. It gets very complex actually, but I'll let based on how everybody's kind of following and understanding, we can get more or less into that. And TFOP is easy to read. But the math gets with, yes, so all the symbols do get confusing because it is a language, right? Math is just a language, and so if you're not familiar with it, you're not used to using it a lot, it just takes time and it takes practice. So distance learning. I don't know what that refers to, but I'm glad it's better. Thank you for letting me know. I'll be interested to know what that is, though. Distance learning. Okay, so before we get into this, I want to show you this book. This is a book that I actually came across. I don't know if anyone was with me, maybe a few of you in here, in a bookstore. I went through a bookstore in the science or the toys department. This is a book I actually ended up buying that day, and it's called The New Way Things Work. So there's a book called The Way Things Work. And this is the new one, and it says, look, from lovers to lasers. So I had to show this because it's actually a really beautiful diagram and certainly better than this mess right there. So yeah, it is a great book. It's by David Macaulay. So if anyone wants a quick screenshot there, you can take that there. Oh yeah, the old one. Yeah, the old one's great too. If you're interested, you can get a copy for yourself. So here is the picture that they have that master's level knowledge from taking courses. You know, honestly, to be honest, that's, I think, a whole other conversation in itself, just because of the way that technology is changing and the way that education is changing. I don't think that's actually quite a straightforward question to answer, but a good one nonetheless. And I think learning is free. I don't know, you know, you don't get the actual, maybe today's accepted the piece of paper, but the actual amount of education you can get, no question, you can get on your own, for sure. So, oops, sorry. So hello, Orion. To review, another quick review yesterday with much better diagrams than I could do. This is the essentials of a laser. You've got your atoms here, or molecules, or crystal, right? I drew a crystal because that's the one I was used to using. And, yep, pretty much tiny mammoths. Here's a mammoth. And the atoms in here, what they're doing is we're exciting these guys, and I'll talk about that a little bit more in just a second. Actually, a lot more in just a second. So if you take it on faith for a couple of minutes, right, we're going to give, these guys are somehow going to have energy ready to give up in the form of light. And when this light from one of these will randomly be de-excite, they call it, or radiate, it has a direction to it. And this nice cavity shape with the mirror here and a mirror here will actually use the fact that this radiation then knocks into his brother right here, and he says, hey, check this out, let's radiate at the same wavelength in the same direction. And then those two guys knock another neighbor or other neighbors, and these collect on top of each other. And then the mirror bounces it back to do even more, and you get what's called a standing wave like this. And, oh, you're knitting and listening. Oh, I love that, Linda. Thank you. So these waves are standing waves in this cavity that's capped by mirrors here, but one of these mirrors lets a little bit leak out. And what's important about that is that what's leaking out here is all the same wavelength, as you see, that's right, this is the same wavelength, all the same, which means the same color or the same energy. It's in the same direction, and it's not going, right, so it's not going all in different directions like a light bulb. And then that is your laser beam. So, oh gosh, what did I do with my laser pointer from yesterday? Should have had that at the ready, huh? Anyway, so that's the kind of the basics of the laser, and then what we're going to talk about today in the quantum mechanics world here is essentially how this is happening inside the laser cavity. So what does it mean to excite these guys here? It means actually that we are controlling, this is the really cool thing, we're controlling the energy that individual atoms and molecules have. And what that means is the energy is absorbed, and those electrons around the atoms or molecules, they've got more energy, right? So they're going to run around in bigger circles, and they're going to take up more space. But the quantum mechanics part, and this is what's really vital, and what gives that one wavelength and that one energy, is that these electrons on molecules and atoms, and this is true of all molecules and all atoms, these electrons, based on the structure inside the nucleus, are only they're only able to take up very particular paths as they orbit around. And if you give this atom an energy that doesn't get it to this next path, it won't absorb it. It won't partially kind of get halfway. It won't kind of try and then give up. It won't see it. It won't interact. Exactly, and I have that at the ready, actually, Victoria. I have Feynman right here ready with chapter 37 flagged. So we're going to do we're going to get from these diagrams to that. So yeah, definitely. So that's the quantum. And so what does quantum actually mean? So I'll come back to this picture here in a second. We'll go back to the board so that we can draw. And by the way, if you're new, I did not do this today, which was terrible of me. My name is Julia. My handle here is Fine Woman, perhaps obviously. I'm also Fine Woman on Twitter, so you can find me there. You can DM me even if you don't follow me. Send me messages during the show if you'd like. You know, if I don't see them or if we're a little off topic, answer them later. This is the website here that as probably frustratingly slowly gets updated because my paid work usually has to take priority, but I do work on it, and I'll put, I've got my Fractal Friday schedule up, and I'll put the rest of, I'll put kind of the laser basics and some information here on that website. So yes, great illustrations indeed. So we'll look at those indeed. So Victoria is, I've gotten her hooked on Feynman, which just makes me giddy as all heck. The other thing I'll quickly mention here is I didn't realize how many people maybe didn't know, but this year, 2015, is the International Year of Light, as declared by UNESCO. And I've even got a sticker here on my glasses case I was showing yesterday, the International Year of Light. And you can go to either of these websites to find even more information. These are two organizations that are kind of the larger organizations when you're talking about light, optics, and things like that. Okay, without further ado, we were, let me erase some of this stuff. Whoops. Still, I love this Adobe software, but I am just slow learning at it for sure. So thank you everybody for your patience. Let's see. Not everything except that, huh? All right, so board is mostly clear. So what we're going to talk about then is these atoms and exciting and what does quantum mean. So quantum, I'll write this here. And oh, and for anyone also who's new, please interrupt me if you don't understand what I'm saying, because I absolutely do not mind. I think it's vital, and if you don't understand it, that probably means other people in here don't, or on the replay will also not understand it. So yes, please feel free. You never said why there are stickies. Oh, I thought I did yesterday. So that just, and I tried to cover it up so it wouldn't be distracting. It's a Dvorak. It's a different way of instead of QWERTY on your keyboard, it's just a different way of laying out your letters and typing. So sure, you'll end up being a fun, that would be amazing, Victoria, and I think that is a wonderful thing to want to be, and I think you absolutely could and will. So quantum here is, I'm going to use really kind of as simple and useful words as I can. It's a chunk of something. So if I could spell chunk, huh? There we go. Chunk of something. So that just means it is an amount. It is a discrete amount of something. So that's another way of saying it. And that means when we're talking about the atom here, we've got our nucleus and we've got our electron circling around in this, for now, a circular. That's kind of the easier way to describe it. They do take other shapes, and that's another quantum process, but we'll get there. So if the electron here, can atoms be excited or change to go in the opposite direction than their normal route? That's okay. So I think if I understand, the direction is an interesting question, because theoretically, so speaking in terms of like a crystal, for instance, a solid, the atom itself, and the nucleus maybe being right the center of mass, the atom itself doesn't have to move positions. What's happening is the electron here absorbs energy, perhaps in the form of light. It has to absorb a very specific amount based on what that nucleus is, and it takes up more space. And so, you never want a spelling bee? No, I definitely did not ever want a spelling bee. So the electron will take up, if a light comes in here, we'll draw it lights, wavy things. The electron will take up more space around the nucleus, but the whole atom doesn't necessarily have to move. Now you can energize atoms and have them move by giving them things like heat, for instance, or you can change their position, but position then also becomes kind of a relative thing. So thank you for that question, great question. But in terms of this, what we're talking about is actually just the electrons taking up more space relative to the nucleus here that it's surrounding and held by.
So the nucleus is really kind of holding this electron in and pulling it inwards. And at the same time, you've got a countering force. This quantum mechanics is telling you that these guys can't really just crash in and annihilate, would be the word. But what you're saying is that the quantum aspect means this chunk, right? This electron can't absorb some amount of energy between here and here. It won't even see it, it won't react, it just doesn't even know it's there. And that is really the heart of quantum mechanics, and that's what makes everything so fascinating, because it would be chunk mechanics. Yeah, and so when it's interesting to see in the kind of outside in advertising and things like that, they talk about quantum this and quantum that. And I would say about 50% of the time, they're using that word incorrectly, because what quantum means is a jump from one very particular state to another very particular state. And if these are not very defined, if these are not perfectly defined, do all the shells move up a level or just... Great question. Yes, so right now we're talking about the outermost electron, but this absolutely, you have lots of electrons, and depending on the nucleus, right, this is a very, very simple diagram to simplify very complex things. It does sound way less intimidating, doesn't it? But yes, exactly, the photoelectric effect, quite right. So if you have lots of electrons, then absolutely you can have one electron absorbing one amount, and then another electron absorbing another amount. But the key thing is these shells, which is absolutely another way that they're described, that these shells have to be, they have to follow the Dirac law of saying you can only have one electron in exactly the same energy state. So no two electrons can have exactly the same energy state. Now, the kind of workaround is you can have two, and they have something called spin, which it's not particularly important for right now, but just to mention it because it's accurate, they draw it as spin up and spin down. So two electrons can have the same amount of energy in one single atom or molecule, but they have to have opposite spins. And once those two are filled, that's it. You can't have two with the same amount of energy and opposite spins, and the same spin. So that's when you have lots of electrons going on, they call it the density of states. It's how many are available, how many of these shells are actually open up so that these electrons can take it, can absorb that energy, and then a lower one can then take this open spot, et cetera, et cetera. So great question. But just so for the quantum part of the discussion, I'll try to keep that a little simpler too. And if I lost you there, please let me know. I'll try to explain some of that a little bit better if you're interested. So this chunk here that we're absorbing is the quantum part of this. And the reason that is so important, and the reason it's kind of frustrating, I suppose sometimes when I see people in advertising and kind of sensationalist material misusing it, is because it is so vital to all of this working, because it says this is very clearly defined by math, and this is where we'll get into the math, Victoria. And this is this other state, if you're going from here to here, so this would be a quantum leap, for instance, of something going from somewhere to somewhere else. Doesn't necessarily matter, but this has to be very well defined in all of its energy, most importantly. And this also has to be perfectly defined. If there's any fuzziness about it, then it's not a quantum leap. And so now you may not be able to measure, that's the other important aspect, right? We can't measure something perfectly, but we can describe its motion perfectly so that we can know aspects about it a little less than perfectly. Pretty close, but a little bit less than perfectly. So this leap here, that's what that electron is doing from one shell around this nucleus to another shell. And so he gets all excited once he's gotten the right amount of energy for available states, they call it. So there's another one here, perhaps, right? I'm not describing any particular atom here, just the concepts. And so if I were to give another electron here, we'll call it, right, he can have a spin down. Are you telling me, Deepak? Absolutely, he misuses it. He misuses it all the bloody time, to be honest, and it frustrates the heck out of me. He does not understand it. So maybe, you know, I guess the spin you can hopefully trust me on without those arrows. That might just confuse things. So if we have another light in here, now the electron can jump straight to this higher level. So how would, well, so that's a good question. I guess I don't really listen to him enough, or haven't listened to him enough lately to be able to correct him. But if you have something specific that he says that you're interested in, maybe tweet me and I'll see if I can clear it up. Yes, a lot of people misuse quantum. Okay, so the other aspect here, this is the quantum mechanics, and I'll start to get into the math, Victoria. I'm sorry, I don't want to take too much time from people. I try to keep this show at least reasonably short. But the exciting here, this electron, if you give it light with this much energy, this being this 2-shell jump, if it's the discrete amount of the jump from shell 1 to shell 3, it'll do it, absolutely. And this is the laser part. So yeah, and the other way to draw these, we were drawing them yesterday kind of like this. And then there was this intermediate state, and we could say, okay, the electron goes from here, and then it goes to here, and kind of hangs out here for a while. That was that really important part of the laser, because you need all of the atoms in that cavity to kind of, you need the electron to hang out here so that all the atoms in the cavity can all be ready to emit at the same time. When I saw a title on YouTube, through a wormhole. Oh, you got confused. Oh, because of the quantum. I haven't seen that show in a long time. But yeah, if there was something in there, please, as you know, Victoria, you can absolutely tweet me. So this is one way to draw the diagram. This is another way to draw the same diagram. So this guy and this guy are just different ways of drawing the same kind of concept. And so we can say, okay, light comes in here. The electron goes from this shell all the way up to this 3rd level. And then from the 3rd level, he's going to eventually relax back down to the 2nd one. Now, to do that, he's got to give off light, and that light is going to be of this amount now, right? That 2nd stage, so that's going to be that guy. And he's going to hang here, and then as that picture in the book, which I can open up again quickly, just because pictures are worth millions of words these days. So here we go. So there's that jump, right? These 3 levels. Then the fallback is the giving off that radiation, and then what we need here for the laser part of it is we need all of these guys to be ready to give off this red light in the same direction that's red in this picture, but the wavelength, the same energy in the same direction. And how do they get ready to do that? And that's called the population inversion in the terms of laser words. And they get ready to do that because they've got this kind of hangout area here. They can kind of hang here for a second and wait for all the buddies to get ready. And so that's the other important part. So you cannot make a 2-level laser is a really interesting topic because it just doesn't work that way. You have to have a 3rd place for it to hang out here. Okay, so now let's get into the math a little bit. I'll try not to make it too crazy and, you know, lots of crazy symbols, but I'll just use numbers because, excuse me, because what you're talking about here is the energies again. And when I said it has to be very defined, this state here that you're going from and to, they have to be very defined because that's the way that the math will allow us to understand this. So if we call this state 1, and again, if you aren't following me, I'm going to kind of let the audience here help, dictate how deep into this we get. But if we call, oh, sorry, I even already kind of messed up. So if we call this state 1, and they usually draw it, you'll see it in books like this. So if you see this, Victoria, or anyone else who's seen this, oh, that's awesome. I freaking love lasers too. Can you pull up the screenshot too and briefly explain it? Oh, the screen, sure, absolutely. So let me see if I can pull out your, the tweet here. So if you see this, but this is really very common in quantum mechanics, this notation here where they'll have a number. Oh, very cool. They'll have a number, 2, 3. I even had a professor in college. She said, it doesn't matter what you write here because you're just describing this place, whether it's, however you want to describe it. Again, math is just symbols. And so he drew this and, we all got quite confused because we didn't understand exactly what he said. He said, you could have a flower state if you want, and they draw it that way. But anyway, that's not quite as important, so we'll get back on track here. All right, you have one state. This is very well defined. You're going to have a second state. We'll draw this as 2, and we can have a third state. Well, sorry, drew it backwards again. Apologies, I really do appreciate people's patience because I'm still learning how to teach some of this stuff live also on a very new app. So, yes, exactly, you got it, you got it. And so this would be the first and the second and the third levels, right, the states. Okay, so the screenshot, let's see if I can pull that up. So here we go. So this is the screenshot that Victoria was asking me about. And you see, so the waves that they're describing here, oh, wonderful. Oh, I'm glad. So the waves that what they're describing here, this is an intensity. So I just means intensity, all these different ways of describing it. This guy I'll talk about just a second, this E, I, omega, or WT, that's, all these are just mean shapes, essentially. And that's why Feynman was so brilliant, because he just got fed up of writing all these numbers. And so he said, I'm just going to draw diagrams. And Feynman's diagrams, that's essentially what he got the Nobel Prize for, because that explained how a lot of the stuff works. And so the cosine here is, here you go, cosine delta, these cosines. That's it's a different way of writing this e to the I omega t, and those are both different ways of mathematically describing, and it's important to do it mathematically because those numbers tell you the energies, they tell you the different, yeah, pretty much, Scott, pretty much. Feynman's QED, a book which I don't have handy, I think it's upstairs, unfortunately, but his diagrams, oh, I hope it's a good frazzle. I really do. So please, yeah, tell me if I'm losing you. But these this cosine of, they call it omega. You can WT. It doesn't matter. T is time, because these are waves moving in time, right? We have no. That's the dimension we're stuck to. And E, the other way to draw it, E to the I. Now that I is quite important actually in math, but these are very related, and actually cosine, I always forget if it's plus or minus, but it's going to be it's true, I do, but I moved downstairs to work here. So, oh, bye Scott, thank you for coming by. Oh no, you're so confused that I'll see if I can unconfuse you. Please tell me where I lost you first, and I'll see if I can kind of reincorporate that. So here we have E, these fancy, and this is a minus sign here, right? Well, I hope, yeah, so maybe if I can keep talking about this and redo these kind of things, and maybe something will stick. And if you only get maybe 1 or 2 things, I can't expect you to get everything, absolutely. I mean, some of this I'm messing up too, so, but if there's something you're interested in and I really do lose you, please tell me. So this cosine is just a way to describe exactly this shape. Cosine means this. And the omega and the t, those represent numbers, whatever numbers you want to put in. You can put in 1.4, and this would have to be a frequency, and so that's in a per time. So hertz is the way to do that, so per time if you want, times whatever you want to say, 2 seconds. You lost your mother. Aw, thank you, Mummy. Well, I've tried, yes, I love you, Mummy, but, after almost 30 years, I think I have to give up. So the 1.4 is just, right, that, for me, I've picked that for W or omega. And the reason that they use all these letters is because this really, for different systems, different atoms, this symbolism is still true. You're just going to have to need different numbers. And that's why this makes it kind of general as a principle thing. Never, okay, I won't. Thank you, Mommy. You're right. I shouldn't. Oh, good. Oh, I'm glad, Victoria. So this omega t, these are just, and this is true of all math, right? They kind of abandon numbers at some point because it's just pointless, since these things apply to so many different systems. So they use letters instead, so that when you get to a specific system, you can plug your own numbers in. And so if we go to our, I think my board's getting a little crowded here. Let's see if I can erase some stuff. Awesome. Okay, so if we draw this curve, now again, you gotta accept that I'm not the greatest artist, but this curve, this oscillation, that every light wave, light is a wave, and that is described by this oscillation, and that's described by either one of these. And I hope I always get the plus and the minus. This is sine and cosine are, and it's actually here. Oh, thank you. Is there a minus I as in a square root? Yes, exactly. So I, and this is the important, so I is the square root of -1. And that has important, very, very important implications in how these waves work. Because in math, you say, okay, what's the square root of 2, or what's the square root of 4? You would say the square root of 4 is 2, and you know that because 2 times 2 equals 4. And the square root of 4 is always going to be 2. But if you think about it, -2 times -2, and I'll try to have this be really the most numbers I use. Also, and I did a dot, but I think maybe that's more familiar for people. So -2 times -2, so that's interesting. It cannot actually. This is also 4. So the square root of 4 is 2. And it will never be -2 because, well, I guess in one sense, yes, you're right. I suppose it could, but -2, how do you describe -2, or the square root of -4, I should say. How do you do the square root of -4? Oops, I keep doing dot, right? Because this is -2 times 2 is going to give you a -4. So minuses cancel in multiplication. And if you only have one of them, then how do you do the square root of -4? Right? Because the square root, by definition, is going to be one number, right? Square root of 4 is 2. It has to be one number because it means times itself, it gives you the number you're looking for. So what's the square root of -4? Well, that's kind of a weird question because you don't have, exactly right, bang on. So the square root of -4 is 2i. And it is because I is the square root of -1. So are we into all that minus, plus, minus? No, not quite. Not quite. So, excuse me. So the square root of -4, and the reason we get this is because that equals the square root of -1 times 2, right? That is the I here. So, oh great, I'm so glad, Lynn. Yeah, and we'll wrap it up here because it's getting a little later in the show, so I don't want to take too much time. But anyway, that I is important, and I can talk a lot. Oh gosh, I could talk a heck of a lot more about that I. It is really quite vital to the way that you describe these waves. But I don't want to lose people too much, and I'll get back into the way that this quantum has to do with the math. So without getting into the numbers again, but. So the square root of -4 isn't plus or -2. Correct. Absolutely correct. Then what was the -I? I'll do a scope on the -I. So -I, let's see, B, here we go. So I is the square root of -1, and a -I is then this minus the square root of -1. And so when you have I times a -I, then you get a, or I should say when you get I squared, this is the important part, so you get I squared gives you -1. That's the big issue here, because then you can get you can square something and get a minus number, right? Because if you square -2, like we said, right, -2 squared is going to be -2 times -2, and that is always going to give you 4. So how do you have a number that you can square and still get a negative number? That's maybe a better way to describe it, going the other way. So I squared is a -1, and so if you have -2 squared, that's not going to give you 4. But if you have 2i squared, that will give you -4. So, negative. Oh, I'm sorry. Is it negative? Yes. I'm sorry. I say minus. So, yeah, so that's this. This is very important. This has to do with, it's called complex analysis. It's actually, when it comes to math and kind of rattling these things off, that is a weakness. So I'll go back, and if I made any mistakes, I'll try to write the notes for the YouTube part. But this is a very, very important concept here. Then minus I, good question, sorry. Minus I is just minus the square root of -1. And the reason that's important is because in these exponentials, it's like saying I minus, or plus rather, a minus or negative I is 0. And that's useful here because then what happens is this equation, that's a bad joke. Oh, sorry. Yeah, I kind of miss the joke sometimes. So that's important for Victoria and what she was showing in this screenshot, because when you describe a wave, I'm going to move this up a little bit if I can, and then don't need these guys. When you describe this as a oscillation, right? If you take two oscillations, and as you may or may not know, right, when we talk about diffraction and things like that, then if you have one wave and you overlap it with another wave that's what we call out of phase, meaning it's the same wavelength, but where you get an upwards going on one, you have the downwards going on the other, then what do you get? You actually cancel. You get nothing. You get a flat line. You get a dark spot, and that's that diffraction. And that comes from the fact that one of these guys is described by this, and then when you multiply it by something that looks very similar, then you're going to get this zero-ness. These I's are going to cancel. So, oh, great. I love to see these cymatics. Now, I'm embarrassed to say I'm not sure if I recognize what that word refers to. I probably should, but please let me know. So, like sound canceling, exactly. Sound is also a wave. So when you have sound engineers that have to be able to, they have to understand where to place the speakers so they don't cancel, this is precisely the math that's describing it, because you multiply another thing that looks like this, and when you, yes, we took the life out of the waves. So when you multiply something that looks like this, let me, if you don't, let's see also, I need a bigger board here, don't I? Here, I'll just do this. Ah, magic, magic, magic. Love it. All right, so when you multiply e to the minus omega it times n e to the I omega it, and so just the way that they've drawn that the math is being represented here. Oh, great! I'm so happy. Thank you so much for stopping by. To get a bigger board, yeah, exactly. So when you multiply just the rule in exponentials, so not, again, don't want to get too much into the math, but when you multiply this kind of thing, then what you end up getting is you have to add what's in the exponent. Yeah, it's true. I'll work on that. So you add this equals e to the minus I omega t plus I omega t, and that's a 0. So better actually, let's see, make this a plus and this we will make a minus, right? So if this is a plus, that's just confusing. Okay, there we go. So if you have this, right, this equals, oh, where's my brush? There we go. This equals e to the 0. And that actually just equals 1. But essentially what you've done is you've canceled this out. You've canceled all the oscillating nature to it, this wave nature to it. So, oh, I missed the headphones questions. Oh, I'm sorry. Please ask it again. Oh, yes, absolutely. Please ask it again. I'm sorry I missed that one. So this is kind of, and this is the quantum mechanics. So when you describe the wave nature of something, you're describing it by these, because they're oscillations, then you're describing it by the very defined, right? These are very defined, these are going to be very defined numbers for your leap here, your state 1 to state 2. And so, and the reason they have to be very defined is because when you add them or subtract them, you get properties like canceling. And that's that diffraction, that weird quantum weirdness of adding and subtracting of the waves in different areas, the phase nature. So, do noise canceling headphones work by canceling out the ambient sound waves? So I believe noise canceling head works, and I don't know exactly how they work, and I can look into that, but I believe that works by pressure, by exactly by adding a constant pressure or constant kind of minimal ambient noise in the opposite direction. And how does it not cancel out the music? So it doesn't cancel out the music because what you're adding is not simply one wave or a set of waves that might interfere discretely. Again, the discreteness, the chunkness of this is really important because you have lots of sets of chunks, which means one chunk could cancel or add to another chunk if they're lined up correctly. Oh, great. Thank you. Thank you so much. Thanks for stopping by. I've seen that you watched the replay, so I appreciate that. Yeah, it sends, but what it does is it sends something called white noise, which is like saying you have this, and then you have this, and then you have this, and you have all of the, oh, you can't see any of that, can you? Sorry. You have the continuum, this mess of all of these different waves. And so on top of that, your music is going to be this very nice set above that, where you have very discrete sets of these frequencies above the noise. And the noise will be kind of a minimal. So more than that, I would have to just take a quick review as to how they work. But essentially, it's white noise going in the other direction into your ear. So yeah, you can see it. Yeah, sorry. It takes me a second sometimes. Okay, so I've probably lost a number of people, and if I did, please don't ever be afraid to tell me that you lost me. I'll try to keep improving on this, but that's kind of where the math comes into the quantum mechanics. That is why the misuse of quantum is really frustrating, because the quantum means you are very defined going from one place to another very defined place. So something in the music is the same frequency as the ambient noise. Well, it will be if it's the same amplitude. That's the other aspect of this. I will check out cymatics, absolutely. I've never heard that word, so I'm fascinated to learn something new. So thank you. Oh, I'm so glad, Victoria. So yeah, so that the noise canceling aspect is an amplitude thing, and so that's to say if you have this wavelength, for instance, and then you have something going downwards with the same wavelength, but it's going downwards more and upwards more. The best ones have microphones to sample ambient noise. Yes, so that's a dynamic thing. So it's constantly sampling and trying to see what this spectrum is that you're trying to cancel and listen. Exactly, great way to put it. Or maybe not, because you. Oh, no. I always, there's so much I don't know. I'm just smart enough to know how stupid I am. I like saying that. So you're talking about the bows. Yes, exactly. Okay, so what I've drawn here, so then this going up and down, this would cancel it, and you'd end up getting a smaller wave than what you started with, but the same frequency, right? So this distance between, again, my drawing is abysmal. I apologize. So you'd get a smaller wave here, but the important part is that this spacing here is the same as this spacing here. But it's just now smaller in amplitude. So that's the volume you're turning down. So when you turn down your music and you turn the volume down, you haven't changed the frequencies, you haven't changed these numbers, omega or T, and you haven't changed the spacing between the waves, and you haven't changed the shape of the wave. What you've changed is the height of the wave, and that is, the other way to write that in this math would be having like a 1/2 out here in front. So that's the amplitude. So if we put a 1/2 out here in front, right, then this wouldn't totally cancel. Here we go. Yeah. So this wouldn't totally cancel because you'd have e to the here, but then you'd also have a, for instance, a e to the 1/2 of I omega t times this, then you'd actually have a little bit left over with that same frequency. So it wouldn't totally cancel, it just cancel in amplitude, and it would bring it down. So that's the difference between coefficients, they call them, or the stuff that goes in front of this letter, and the stuff that goes in the exponent, or the stuff that goes in the superscript of this letter. So the superscript math acts a little differently than the coefficient stuff in front. No, that's fine. I'm going to wrap this up actually. I'm going to wrap this up now because I try to keep it half an hour. I usually go to 45 minutes, but look how fun this was, huh? This was a mess. But I hope some people followed. So what does amplitude mean? Amplitude means volume, or it means height. It means the largeness of something or the smallness of something, but mostly the largeness. Oh, I'm so glad. I'm so glad it made sense in the headphones. Yeah, absolutely, absolutely. So that's the quantum part of all this laser, and that's why it's so important, because when you're controlling these atoms and what light they're going to give off, you have to understand the molecules, the nature of the molecules, and what the numbers that you can plug in here are going to be, so that when you get the light that goes in, also described by this kind of thing, that the light that comes out, which will be described by this kind of thing, but with different numbers in here, you can control these processes to give you the light the way that you want it. So, yeah, exactly. Yeah, great way to say it. Similar to altitude, kind of. Oh, sure, of course, of course. Hey, Zebra, nice to see you, nice to see you. So unfortunately, yeah, we're wrapping up. This got very complex, as you can see. Look at all that fun. But hopefully, at least people kind of got something out of it. And then tomorrow, I'll talk, I can either answer some more questions about this, or I can talk, I'll talk about the applications of lasers when they're used, like different types of lasers. Oh, and I was going to show, sorry, I'll just quickly show the Feynman lectures, because that would have been probably a better place to start. Chapter 37 as Victoria, so, and I'll turn it around to say hi so you can see who's talking to you all this time. And let's see, energy levels, here we go. So let's see, quantum measurement of position of momentum, so the quantum stuff. Hi everybody. Okay, this size of it, and where is he? Oh, I'm in chapter 38, that's why. Quick, sorry. So experiment with bullets. Yes, so what he's describing here is the interference and watching electrons. So I'm sorry, I should have looked through this a bit more, Victoria, because I didn't realize that your screenshot was from exactly this, but here we go. Hey, Simon. So here we go. So this is in Feynman, so he's talking about the energy levels here, if it'll focus. Yeah, the energy levels here. And yes, this is chapter 37. Oh, I'm so glad, thank you. Oh no, I went to 38, I skipped ahead a little bit. But the energy levels here, we're talking about this E3, E2. Now that H bar is very important, but not for the discreteness aspect for right now, just for this part of the conversation. But essentially what he's describing here, this omega, talking about the energies, that's these energy levels that we were drawing, this electron going from one to another and back and forth and then giving off light. So several different possible transitions. That's another way to describe it. So I'll try to, if I can, yes, 37.5. I saw it and it was right here, but I couldn't find, let's see. Couldn't find, this is I think what the screenshot was from, right? And I couldn't find kind of what I was looking for. Here we go. So we have the I omega t. So these are the coefficient part, height 1, height 2. And the intensity, so intensity is amplitude, is very, so intensity and amplitude are synonymous. That's actually so a good, an important part. The intensity, the amplitude are synonymous, and that's why that's the coefficient part that goes out in front and not in that exponent part. So the intensity here, you're talking about the amplitude of the wave. But that cosine, right, that cosine nature of it, that's what is this I omega t part, and that is what doesn't change for this particular, I think, for this particular discussion here. So I'll reread that and make sure that what I say is correct. I'll tweet you if I said anything wrong. But yeah, I'm trying. This is actually great. This is actually great for me because I'm trying not to forget this now that I'm doing more of the writing. I'm not in a lab so much every day and studying this stuff. So this is selfishly good for me as well. So, okay, great. And I will too, Victoria. And if you have any more questions, again, always feel free to tweet me. Everybody should always feel free to tweet me. So thank you again. So this is part 2, a little longer than usual, but you know, quantum mechanics, you can't. So I think somebody said, what is quantum mechanics in a nutshell? Hi, Orion. So I think the only thing I could say in a nutshell would be it just means chunk, but when you're talking about waves and lasers, it gets a little bit more complicated, so we went over a little time. I hope I didn't take too much of people's time. But I will upload these eventually. I'll upload the set, the part 1, 2, and 3 here. And no, please don't, Victoria, please don't. Just don't. I hope you don't mind if I don't get to them for a little while. Of course, thank you, Mike. Thanks so much. And again, thank you also for the tweets. Oh, I'm so glad, Ander. Thank you. Oh, I appreciate it. Everybody have a wonderful day. And then tomorrow we'll talk about the different types of lasers and how they can be used in applications and stuff. And then I can clear up any of this if people are interested and ask questions. So, thank you. That is really my goal. I'm trying to make it less intimidating, really, because it doesn't have to be. I think it can be very easily with these, quantum teleportation, entanglement, photon, big words that mean a lot of the similar things. And if you say chunk, maybe it's hopefully a little easier to swallow. So thanks again, everybody. Have a wonderful day, and we'll see you hopefully tomorrow, same time. And that's 12:30 Eastern, 11:30 Central, 9:30 Western, yes, Pacific. And catch Linda Knits here at 2 p.m. Eastern. Ian has his show a little earlier. I missed it this morning, so I'm going to watch the replay. Some great shows. Bye, everybody. Oh, wonderful. Great. I look forward to seeing you all then.